All right, so let's go ahead and get going. Today we're going to start a new unit of vectors. So we'll talk about quite a bit of things today, introducing you to vectors. We'll talk about vectors being directed line segments. We'll talk about component form and linear combination form. We'll talk about performing operations on them, both algebraically and graphically, and talk about direction angle of vectors as well. And we'll see how they can be used. Okay. So, as it says here, right, many quantities in geometry and physics, such as area, time, and temperature, can be represented by a single real number. Other quantities, such as force and velocity, involve both magnitude and direction and cannot be completely characterized by a single real number. To represent such a quantity, you can use a directed line segment. The directed line segment PQ, that should say, has initial point P and terminal point Q. Right? Its magnitude or length is denoted by, and that's called the magnitude of PQ. It's the double bars around the name of the vector. Right? And it can be found using the distance formula. All right, so when we talk about the magnitude of a line segment, all right, it is actually the distance of the line segment. All right, that's very important to note. All right, so when we talk about this directed line segment here, all right, it has an arrow on it, kind of like we do when we graph lines, but it does not mean that that line segment goes on forever and ever. Okay, the arrow is simply to tell us which direction it is going. All right. So when you graph a vector, do make sure that you don't just kind of do it really short or really long like it is supposed to be specific in actual length. All right. Two directed line segments that have the same magnitude and direction are equivalent. All right. For example, the directed line segments below are all equivalent. Right. They all are the same length and they're all going the exact same direction. So it doesn't matter that they're not in the exact same space, right? The only thing that matters is direction and length. So it doesn't matter where they are, they're still considered equivalent. All right, and we often denote vectors by boldface lowercase letters, often U, V, W, so on. Those are the most commonly used names for vectors. All right, so let U be represented by the directed line segment from P, the initial point, 0, 0, to Q, the end point, 3, 2. And let V be represented by the directed line segment from point R, 1, 2, to point S, 4, 4. All right, so show that U is equal to V. All right, well, we just said that in order for U to be equal to V, they have to have the same magnitude and the same direction. Okay, so first we'll talk about magnitude. All right, magnitude is essentially, like we said, just the length. All right, so we can get that from the distance formula. Whoops. Let me get the pen going on here. All right, so our distance formula, hopefully we remember, d is equal to the square root of x2 minus x1 plus y2 minus y1, right? And this was from Algebra 1, geometry, all of that kind of stuff. All right, so first we want to do, we'll do from P to Q here. All right, so the distance here is going to be equal to the square root, all right, of, oh, come on. Son of a biscuit. All right, so the square root of 3 minus 0, whoops, and I forgot up here, these are squared. This is essentially just found from the Pythagorean theorem. All right, so 3 minus 0 squared plus 2 minus 0 squared. Of course, this is all under the square root. So this then just equals the square root of 9 plus 4, which of course is the square root of 13. All right, so there's the distance or the magnitude, all right, of vector u. Remember, we do denote that like this. This would be the magnitude. All right, so now we can do that down here as well. All right, so the magnitude of vector v will be equal to the square root of 4 minus 1 quantity squared plus 4 minus 2 quantity squared, which is equal to, again, 9 plus 4, which is the square root of 13. All right, so now we know that their magnitudes are equal. All right, now a little bit later we'll talk about how to actually find the direction angle of the vector, like actually given in degrees. All right, but we don't know that yet. So for right now, to show that they're going in the same direction, we're just going to go ahead and use slope. All right, so up here, the slope of vector u, all right, is going to be y2 minus y1 over x2 minus x1, all right, and that is going to be 2/3. And then we can also find the slope of vector v, all right, and that's going to be y2 minus y1 over x2 minus, I'm sorry, I did that. There should be 2 here. All right, so y2 minus y1 over x2 minus x1. All right, and here we will get, again, 2/3. All right, so since their magnitudes are the same, and in this case, technically, we would never really use slope to show that they're going in the same direction. Eventually, we'll be able to find that actual angle. All right, but for now, that's good enough. So we can say that vector u, all right, is equal to vector v. A vector whose initial point is the origin can be uniquely represented by the coordinates of its terminal point. Right, and we would call that v1 comma v2. All right, this is the component form of a vector v. All right, and we write that by simply using those coordinates and putting these kind of sharp brackets around them. All right, like I said earlier, right, any vector that has the same magnitude and same direction, all right, are equivalent, and it doesn't matter where you put it, right? So why don't we just always put the initial point at the origin, and that will make it a lot easier for us. So whenever it's in component form, that just means that, okay, well, the initial point is at the origin, and then this is just the coordinates of the end point, okay? So the coordinates v1 and v2 are the components of vector v. If both the initial point and terminal point lie on the origin, then v is called the zero vector, right? And the zero vector obviously just has the component form of 0, 0. The component form of a vector with initial point P being P1, P2, and terminal side, this should be terminal point, Q, Q1, Q2, is given by the vector PQ, and to get that in component form, all we have to do is do our P1 minus Q1, P2 minus Q2, and that will give us our component form V1, V2. The magnitude or length of vector v, is given just like we did before using the distance formula. So P1 minus Q1 squared plus P2 or Q2 minus P2 squared. Which once we have it in component form, it's actually much easier. All we have to do is V1 squared plus V2 squared. If the magnitude of v is equal to 1, then v is what we call a unit vector. The magnitude of a vector is equal to 0 if and only if v is the zero vector. So if you're dealing with any vector other than the zero vector, it will always have some actual magnitude. Two vectors u and v are equal if and only if their corresponding components are equal to each other. So if we have vector u being equal to u1 comma u2 and vector v being equal to v1 comma v2, then if their first components are equal and their second components are equal, then we say that the vectors are equal. Okay. The two basic vector operations are scalar multiplication and vector addition. So if we have two vectors, vector u, which is equal to u1, u2, and vector v, which is equal to v1, v2, those are two vectors, and k is a scalar, which is just a real number, then the sum of u and v is the vector u plus v, which all we do is add their first components to get the first component of the sum vector, and add their second components to get the second component of the sum vector. And the scalar multiple of k times u, so if we have k times some vector u, remember k is just a real number, 2, 7, negative 5, all you have to do is multiply that by each of the components. Okay, so let's look at a couple of examples here. Let v be the vector negative 2, 5, and w be the vector 3, 4. Find the following. First, we want to find 2v. So that's just a scalar multiple. So all I have to do is say that this is going to be 2 times the vector negative 2, 5. So all I have to do is essentially distribute this. So I'm going to get the vector negative 4, 10. Here we're going to have the vector 3, 4 minus the vector negative 2, 5. So all we have to do, is subtract their corresponding components. So 3 minus negative 2 would give us 5, and 4 minus 5 would give us negative 1. That's it. For C here, to find v plus 2w, all I have to do is negative 2, 5 plus 2, times 3, 4. All right, order of operations still apply here, so we need to do multiplication before we do addition, so we can just keep this one for the time being. And then when I go ahead and do my scalar multiplication here, we will get 6, 8. All right, well now I can go ahead and do my addition. So negative 2 plus 6 is 4, and 5 plus 8 is 13. So 4, 13. And that's it. So basic operations on vectors, really not all that difficult. It's very intuitive and just kind of makes sense. All right, here are some properties of vector addition and scalar multiplication. These aren't really super important. All right, not a huge deal by any stretch of the imagination. This is just saying that vector addition is commutative, which means the order doesn't matter. All right, this is saying that vector addition is associative, which means when you have multiple different items, right, that the order in which you group them doesn't matter. All right, this is just the identity property, right, just saying that if you add 0 to any vector, you end up with that same vector. All right, this kind of comes from that same property, right? If you add the opposite of a vector to a vector, then you just end up with 0. All right, this is saying that scalar multiplication is commutative, so it wouldn't matter which order you multiplied. You can either multiply the scalars first and then multiply it by the vector, or you can multiply one of the scalars by the vector, then the other one. It's not going to matter. Here we have the distributive property, essentially, right? So the scalars c plus d as a group times u is equal to c times u plus d times u. All right. This again is the distributive property, but now we just have one scalar with two vectors. All of this stuff really just kind of makes sense. It's nothing that you need to memorize or know. All right, of course, 1 times any vector is itself, 0 times any vector is 0. Again, very kind of intuitive. All right, and here the magnitude of some scalar c times a vector v, all right, is actually the absolute value of c. This isn't a typo. This is the absolute value, since we're talking about a scalar here, times the magnitude of v. That's the only one that's not very kind of intuitive. Okay, so earlier we talked about a unit vector is a vector with a magnitude of 1. All right, so you can make any vector a unit vector that's going in the same direction of the original vector simply by taking the original vector and dividing it by its own magnitude, right? Which of course is the same thing as multiplying it by 1 over its own magnitude. All right, so it says here, note that u is a scalar multiple of v. The vector u has a magnitude of 1 and is in the same direction as v. All right, the vector u is called the unit vector in the direction of v. All right, so find a unit vector in the direction of v and verify the results has a magnitude of 1. Okay, so we know that a unit vector, u, is simply equal to the vector divided by its own magnitude. All right, so first we're going to go over here and find the magnitude of v, which again, remember, is just the length. All right, so this is the square root of negative 2 squared plus 5 squared. So this is the square root of 4 plus 25, which is simply 29. All right, so all we have to do here is say, okay, well, then this is going to be negative 2, 5. All right, and this will just be divided by the magnitude, which we already found is the square root of 29. So this really just equals negative 2 over root 29, comma 5 over root 29. Right, of course, you could rationalize this. I'm not overly concerned with that, but just for explanation purposes. Okay, so there's our unit vector. All right, well, now to verify that it has a magnitude of 1, all right, we again use our formula here. So this would be, and I'm going to go ahead and use this one because it's actually going to be a little bit easier. So I will say negative 2 over root 29 squared plus 5 over root 29 squared. All right, so now when you square a fraction, you square the top and square the bottom. So we are going to get 4 over 29 plus 25 over 29. And of course, when we add these, this is going to be the square root of 29 over 29, which is the square root of 1, which is equal to 1. So obviously, that has a magnitude of 1. All right, since this is just another example of the same thing, we will go ahead and skip this for time purposes. The unit vectors 1, 0, and 0, 1 are called the standard unit vectors and are denoted by I for the vector 1, 0 and J for the vector 0, 1. These vectors can be used to represent any vector v equal to v1, v2, which is in component form, as follows. All right. Essentially, you just take v1 and you put an I after it, and you take your v2 and you put a j after it. All right. Of course, those are added. Of course, if your v2 is negative, this would be a minus. All right. The scalars v1 and v2 are called the horizontal and vertical components of v, respectively. All right. The vector sum v1i plus v2j is called the linear combination for vectors I and j. Any vector in the plane can be written as a linear combination. Like I said, it's really easy. Don't make it harder than it is. If it's in component form and they want it as a linear combination, you literally just take the components, multiply them by I and j, separate them with an addition or subtraction if v2 happens to be negative. All right. Now, it is also important to note when you add vectors, all right, graphically, all right, so we've already done it algebraically, and so I'm just going to go ahead and say, okay, well, if v is equal to negative 2, 5, and if u is equal to 1, negative 2, all right, then we know that u plus v, or v plus u, doesn't matter. All right, all we have to do is add their components. So negative 2 plus 1 is negative 1, and 5 plus negative 2 is 3. Okay, so of course we've done that algebraically before. It's also important to note that graphically, all right, so if we were to graph these vectors, all right, negative 2, 5, remember we're always starting from the origin. So negative 2, 5 would be somewhere up here. So this would be my vector v, all right, and 1, negative 2 would be somewhere down here. All right, so this would be my vector u. Okay, well, now, if you really just want to, oh, come on. There we go. All right, you can actually just take this and put them end to end, all right? And then wherever this endpoint is, you'll actually get this, right? So if you put them end to end, negative 1, 3 would be this point right here where the vectors end, all right? And you'll get a lot of practice with that, just being able to drag vectors around and add them graphically like that on Delta Math. Delta Math does an excellent job of showing that, but I just wanted to throw that in since I didn't quite do it when we did vector addition earlier. Okay, so let U be the vector with initial point 2, negative 5 and terminal point negative 1, 3. Write U as a linear combination of the standard unit vectors I and j. Okay, so we can still kind of do what we did before, all right, where we say, okay, well, U can equal 2 minus negative 1, comma, oh, then it should be the other way around, sorry. Son of a biscuit. No, there we go. Okay, so now U is going to equal negative 1, whoops, son of a biscuit. This is really weird. Sorry guys, this is my first time using this pad that allows me to write on this software. All right, so I have negative 1 minus 2, comma, 3 minus negative 5. All right, so this would be in component form. So negative 1 minus 2 is negative 3, and 3 minus negative 5 is 8. All right, so we've done that before. Well, like I said, if you want to put it as a linear combination, really all you have to do is take my first component, put an I after it, and put a plus there. Take my second component and put a J after it. So that's it. All right, so this is really the same thing as putting it in component form. It's just called as a linear combination. All right, and basically what they mean here, why they say it's as a linear combination, all right, because since I is just the horizontal, right, and it would be 1, 0, which would be over here, and of course if you multiply that by negative 3, you would get negative 3, 0, so you would have this piece here, right, and then 8j would be my horizontal or my vertical component, so that would be like way up here somewhere. All right, and then of course son of a biscuit. Like I said, still trying to figure this stuff out. Nope. Nope. All right. If I took either one of these, it wouldn't really matter, and move it and put it at the tip of the other one, all right, then when I want to draw and I connect these. All right, this is actually my vector u, and these are my two components of vector u, right? So this would be the negative 3i part, this would be the plus 8j part, and then this green piece here is just the whole vector u, okay? So when they call it a linear combination, that's what they mean, right? Literally two lines being added together, which is just a linear combination. All right, so essentially the same thing again, right? We would just do -8 minus -2, which would be -6, 3 minus 6, which would be -3. So we'd have -6i minus 3j. Call it a day. Okay, so vector operations work the exact same way. All right, so if we're finding 2u minus 3v, first we can find 2u, and we just simply multiply u by 2. So this would be -6i plus 16j. All right, and 3v, we just multiply v by 3. So you get 6i minus 3j. All right, so now when you want to subtract these things, so 2u minus 3v, all right, we say -6i minus 6i, so -12i, and 16j minus -3j, so plus 19j. And that's it. We're done, right? So vector operations work the same way whether you have them as a linear combination or in component form. And we don't need to do it. No, that's the same one anyway. Okay, so now we can talk about direction angles. All right, so if a vector u is a unit vector such that theta is the angle measured counterclockwise, how we normally measure angles, from the positive x-axis to u, then the terminal point of u lies on the unit circle. And you have u is equal to the component x comma y, which we know on the unit circle is equal to cosine theta comma sine theta, since the x coordinate was cosine and the y coordinate was sine. All right, so this is in component form. Of course, this is as a linear combination, essentially the same thing. All right, the angle theta is the direction angle of the vector u. All right, so sometimes you can actually just be, instead of being given an initial point and a terminal point, or having a vector given to you in component form or as a linear combination, you can actually just be given the magnitude and the angle, and that will suffice as well. Again, you'll see this stuff on Delta Math. They do a great job of the visualization of it all. All right, so this is all a bunch of stuff that you really don't need. All right, what you really need is this right here. All right, tangent of theta is equal to b over a. Okay, so of course, if we want to find the angle theta, we would simply just take the inverse tangent of both sides. All right, so theta would equal the inverse tangent of b over a. Now, you have to be really careful about this, right? Because remember that the inverse tangent has a range of negative 90 degrees to positive 90 degrees. So if it's somewhere in quadrants 2 or 3, you're going to have to make adjustments for that. Good thing about tangent is its period is 180 degrees. So you can really just add 180 degrees if you know it's supposed to be in another quadrant, right? Like if you know that you're supposed to be in quadrant 3, the inverse tangent will give you a negative angle, which will put you in quadrant 4. If you just add 180 degrees to it, that'll give you the angle that you want in quadrant 3. If you know you're supposed to be in quadrant 4, the inverse tangent will give you a positive number, which will be in quadrant 1. In quadrant 3. It'll give you, if you know you're supposed to be in quadrant 3, then the inverse tangent will give you a positive angle, which will be in quadrant 1. You add 180 degrees again, and it'll take you to quadrant 3 where you want to be. Okay. Now, if they're asking for an angle between 0 and 360, and you're given that negative angle, which is in quadrant 4, like if you know you're supposed to be in quadrant 4, don't use that negative angle, just simply add 360 to find the coterminal in there. We'll do some work with that here in a moment. Okay, so find the direction angle of each vector. Okay, well, this is my A and this is my B. All right, so we know that tangent of theta is going to equal B over A, which is just 1. Okay, well, now, all right, uh, and remember, this is really the same thing also as 3, 3. All right, so if we think of that graphically, right, the point 3, 3 would be up here somewhere. So this would be my vector. All right, well, I know that I'm in quadrant 1, okay, which is good. You could go ahead and do your inverse tangent here in your calculator. Of course, this is a value on my unit circle, so we should actually know quite easily that this is going to be 45 degrees. Okay, now what I was kind of talking about earlier, all right, let's just say instead of doing this, all right, what if V were equal to negative 3i minus 3j? Okay, well, if we were to graph that, right, negative 3 would be the point here, so my vector would actually be here, right? But if I did my tangent of theta thing again, all right, I would get b over a, which of course is just 1 again. And if you did your inverse tangent, right, it would again tell you that theta is equal to 45 degrees. Well, obviously, this is not 45 degrees, right? It's a lot more than that, but we know that our period of tangent is 180, so if we just add 180 degrees to that, we get 225 degrees. All right, so that would actually be my angle here. All right, so that's what I'm talking about. You can use your, you know, your A and your B, or if you think of it in component form, your X comma Y. That'll tell you what quadrant you're supposed to be in. So obviously, if you're not in the right quadrant, like we weren't here, just add 180 until you get to where you want to be. All right. Now, I do kind of want to go back to this here. All right, so if we wanted to do this again, all right, we say, okay, well, tangent of theta is equal to b over a. All right, so this is not on my unit circle, all right, so I know that I'm going to have to do my inverse tangent here. And if we do that in degree mode on our calculator, we're going to get negative 53 degrees, roughly, all right, rounding to the nearest degree. So we'll say negative 53 degrees. Okay, well, I know, all right, that 3, negative 4 should be down here. Okay, so negative 53 is here, all right, so that is correct, all right, but if I'm told to give an angle between 0 and 360, all I have to do is add 360 to this, all right, and we would get, what's that, 307 degrees, right? So going this way, yeah, that makes sense that that would be 307 degrees. So that would be our direction angle. Okay. So I'm not going to go ahead and do all of these. Let's see, 6, 6. Okay, I will do this one here. All right. So again, I know that tangent of theta is equal to b over a, which is negative 1. All right. Well, again, we kind of want to see where this would be. So negative 6, 6 would be up here somewhere. All right, of course, if we did the inverse tangent, that would give us negative 45 degrees. Again, that would be down here somewhere. All right, well, that's fine. All I have to do is add 180. All right, and that'll give me 135 degrees. Of course, this you could probably do just from the unit circle, knowing that tangent is -1 at 135 degrees and 315 degrees. Okay, so but just do be mindful about that. Inverse tangent will always give you a positive angle here or a negative angle here. So if you're in the second or third quadrants, right, you'll just have to add 180 to get where you want to be. Okay, so find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 30 degrees below the horizontal. So they give us a picture here, and obviously over around here would be 180, so 30 degrees below that, they give us this angle of 210 here. The speed, all right, we can actually consider as the magnitude, okay? So they want us in uh, in component form, right? So how we can actually do that, right? We can actually say, okay, well, here, if we're given a degree and a magnitude, all right, we can say that it is the magnitude of V times cosine theta, comma, sine theta. All right, so this is an important formula here. All right, so we know that our magnitude is just 100. All right, and cosine, the angle that they give us here is 210 degrees, comma, sine of 210 degrees. Now, these are nice because they're on the unit circle. So the cosine of 210 degrees is negative square root of 3 over 2. And the sine of 210 degrees is negative 1/2. So if we just go ahead and multiply these both by 100, we're going to get negative 50 root 3, comma, negative 50. And now it's in component form. We're done. All right. And I'll put a formula sheet up on Google Classroom under materials that has a lot of these formulas that we've talked about today. So you'll have them all in one place, which should be nice. All right. All right. So these are those problems that you might see on a SAT or ACT that people hate typically. All right, so an airplane is traveling at a speed of 500 miles per hour with a bearing of 120 degrees at a fixed altitude with a negligible wind velocity. As the airplane reaches a certain point, it encounters a wind blowing with a velocity of 70 miles per hour and the direction north 45 degrees east. All right, so it gives us a picture here, right? This is the way that the plane is flying originally, and then this wind comes at it this way. Of course, remember that you can just take those vectors and put them end to end, and that will create our new final vector. All right, so what are the resultant speed and direction of the airplane? Okay, so first, in order to add them, right, we can't just add the magnitudes and add the angles, okay? It doesn't work that way. So we're actually going to want to put them in component form first, because then it's really easy to add them. All right, so V1, all right, is equal to, and what was the speed of that plane? 500 miles per hour. All right, so this will be 500 times cosine of 120, comma, sine of 120. All right, so cosine of 120, let's see, that is on my unit circle, right? So cosine of 120 is negative 1/2, and sine of 120 is the square root of 3 over 2. All right, so this is going to be negative 250, comma, 250 times the square root of 3. So that's my V1. All right, my V2 is equal to 70, because there's a 70-mile-an-hour wind, times the cosine. Now, if it's 45 degrees northeast, that's 45 degrees here, which is actually just 45 degrees. So that's a nice one. And then comma sine of 45 degrees. All right, so now cosine of 45 and sine of 45 are both the square root of 2 over 2. So 70 times the square root of 2 over 2 is going to be 35 root 2, comma 35 root 2. Whoops, that should be 35 root 2. Okay. Now, of course, we can't really add these things because, they have different radicals and stuff. So we're going to want to put them in decimal form. So V1 plus V2 is going to equal. All right, so if we just do in our calculator, negative 250 plus 35 times the square root of 2. All right, we're going to get negative 200.503. So negative 200.503. And then when we say 250 times the square root of 3 plus 35 times the square root of 2, that is going to be 482.510. All right, so there's our vector, but it wants it in the resultant speed and direction. Well, speed is going to be my magnitude. Okay, so to find my magnitude, that's when I do the square root of this thing squared. So negative 200.503 squared plus 482.510 squared. And when I do that, we get 522.511. So that's the speed of my airplane now, because the wind is helping us a little bit. All right. And then to find the direction angle, right, we know that tangent of theta is equal to B, which is 482.510 over A, which is negative 200.503. So when I do my inverse tangent of that, right, we get negative 67.435. So we'll just say 67.4 degrees. All right, well, that's obviously in quadrant 4. I know from this picture that I'm in quadrant 2. So if I add 180 degrees to that, all right, I get 112.6. All right, so there's my direction angle, and here is my speed. And that's it. All right, of course, we don't need to worry about that. Your homework will be on Delta Math. So we can go ahead and quit out here. All right, does anybody have any questions?